What I want to do now is to go through that last class, the one that represents the deck of cards, and we're going to call that one class card deck, as you can see up here. We're going to assume a default deck size of 52. And then we're going to have a property that is actually a string array, and we're going to call it the pips. Rather than using actual graphics characters, we're just going to use simple text characters to represent the cards. And as you can see here, the ace is treated as low in this game, and the king is treated as high. And then we have everything in between. And we do that for spades, hearts, diamonds, and clubs. And these then represent array elements 1 through 13, 14 through 26, and so forth. And you'll notice this empty element right here, that's the 0th element of the array. And the reason is because we don't want to start this pip scheme, if you will, with element 0. We want it to start with 1, because in every case we want modulo this index number to represent the card. So since this is the first element of the array, the ace of spades, that index 1 modulo 13 gives us 1, and that becomes the ace. If I do this one, it's the ninth, if we do this one, it's the 9th element, so that index, which is 9 modulo 13, gives us 9, and we know it's the 9 of something. And then we have to treat the king as a special case, because the king represents the 13th element, and the 13th modulo 0 has no remainder, and so we know that that special case when it's 0 is the king. Likewise, if we come down here and look at the ace of hearts, 14 modulo 13 is still 1, so we know it's an ace. But if we divide it by 4, we can figure out which suit is actually being looked at. So we can take this position, divide it by 13, and if it's greater than 1, we know that we're in the second row. So we can determine by dividing by 13 whether we're looking at the spade suit, the heart suit, the diamond suit, or the club suit, based upon whether we get 0, 1, 2, or 3 for that particular pip. So by using modulo, we can figure out the specific card, and by using division, we can figure out the suit. It makes it a fairly easy way for us to manipulate the index and extract information from the index. The index here is actually doing triple duty. It's telling us the suit, it's telling us the card, and it's also telling us the index number of the card. And we can use all three of those pieces of information in our processing. All right, the next thing that we have are property members. Again, we make all of those private because we want to follow the rules of encapsulation and keeping everything quiet to ourselves. Here we're defining a deck, and we're defining it as an integer array object, and we're setting it to deck size plus 1. Well, it's 52 by default, that's the deck size, and we're adding 1, and the reason is because we have this little null guy here. So we need 53 elements to get our 52 cards, because we're throwing the 0th element away, and we're really not using it. So our deck is actually a deck of 53 cards, of which the first card doesn't have any interpretation. And then pass count was put in actually to try and get some feel for the efficiency of my shuffle algorithm. Every time I go through a pass through this one loop, I increment this pass counter, and I wanted to get a feel for how long it took to shuffle a deck of cards. And actually, it's fairly quick. Might not be the most efficient, but I don't care about efficiency when it comes. If it takes 4 nanoseconds versus 8, probably not going to be able to tell. Class card deck, this is just the constructor, and I set the next card to be 1. In other words, I don't want to look at the 0th card, and if I don't set next card to be equal to 1, the compiler initializes it to 0, and that would mean up here I would be looking at this blank space, and that's not what I want to do. So I'm going to set next card in the constructor equal to 1, and that's the only thing that I really worry about. You should be able to tell me now why I made this static. The reason is because it is created, this array then is created at load time. It's not created at runtime when it actually calls for an instantiation of the object. This particular element will already exist regardless. And in fact, if you never called this class, you will still have this pips array in memory, even though there's no object that you've created in the program. So we get that particular array created at runtime, and it's not created on the stack, it's created in the heap. So it's automatically available, and we only get one of them. So we don't duplicate this array every time that we create a new class card deck object. We only get one of them. And why not? It's a read-only array. We're not going to change it. We're not going to change the state of the class card deck object by changing this array. So there's no reason to duplicate it. Deck size, we can return the deck size. It's possible to change that if you wish. Now, this is one of those things where I have this set as public, so this becomes a property method. But what's missing? What's missing is there's no set routine. So this turns out to be a read-only property. If you want to play another game like Euchre that doesn't use a full deck, or you want to play Canasta that uses double decks, you would have to add a set routine in here, because right now there's no way for you to change deck size. All right, next card. Next card is simply going to return what is the index number of the next card. In other words, next card is going to serve as an index into this pips array. And we set it to 1, so we skip over the null. So next card is always going to be equal to whatever the next card in the deck is always going to use this next card as its index. We have the ability to set that because sometimes we might want to deal from the bottom of the deck or something like that. And if that's the case, then we have to have it greater than 0 because we don't want to look at that 0th element, but we want it less than the length of the deck array. And we know that that's less than or equal to the deck array because the deck array has 53 elements in it. If it's within that range, then we can set next card to the value that was passed in. And value, of course, must be an int because this ghost variable called value will be used to set that particular variable. Pass count returns an integer variable. It returns the number of times that I went through a loop to try and shuffle a deck of cards. And there's no reason to ever set it, so I just leave it as a read-only type of property. Helper methods, I don't have any helper methods in this class. And it would seem then that this is extraneous, but actually this is a piece of documentation. This tells you, and I didn't forget to call something a helper method, I simply don't have any helper methods. So yeah, it's an unnecessary line in the program, but it does document the fact that there are no helper methods. I would get in the habit of putting helper methods, property methods, general methods, so forth, in a shell template for your classes. Pull that in and have those comments already built into the template. Now this is my shuffle the deck algorithm. I gave several card game assignments when I was teaching, and I'll bet you if I had 30 students in the class, I would get 25 different shuffle algorithms, unless they went to Google. Then everybody tended to use one of the ones that you can find on Google. But if they thought about it themselves, what you really got was a great variety of ways to shuffle a deck of cards. This particular library routine generates a random number, and that random number then gets seeded automatically. I set the pass counter to 0. That's why I have it read-only as a read-only property. And I set the index to 1 because I want this to start. I want the index into the pip array, or to the deck array, to start with the first card, not the 0th card. That way, the pips array and my deck of cards will align with one another. And I don't have to worry about syncing up those two arrays. Okay, this should be over here. Okay, now, while index, and index starts at 1, is less than deck length. So what we're going to do is we're going to spin through this while loop as long as index is less than 53. Okay? Now, this random number, we're going to get the next random number, and it must fall between 1 and 52. Because deck size is 52, I have to add 1 onto it, so that will guarantee then that the random number that comes back is going to be between 1 and 52. And that becomes the value. What we're doing now, suppose that the value comes back to be 5. We then go into my deck of cards, not the Pip's deck, but my deck of cards, and I ask, is there already a value in here? Because our cards run from 1 to 53. If it's 0, that means that we haven't used that particular element. If that's the case, index, which is currently 1, gets put into position 5. So the first card in my deck is the 5th card, which means it's the 5 of spades. So what we're doing in that first position, in the 5th position rather, is we're writing a value of 1. So the 5th position in our card is going to be the 5 of spades. And we increment index. And the reason is because we've shuffled 1 card into the deck. And I up pass count just so I have an idea of how many times I've gone through this deck. Then I go back, and since index now is equal to 2, it's less than the deck length, so I go through this iteration again. And maybe it comes back with 40 as the value. Then I go look at my deck, and I look at element 40, and I say, is there a card already there? And if the answer is no, then I take a 2, and I put it in the 40th element of the array. So that now becomes that particular card, and I up the pass count. And I keep going and spinning through this array until my index has been incremented to 52. I've placed 52 cards in the deck. So this is worth going through one time. So let's run the program and take a look at how this is happening. Now, you'll see that we have stopped at our breakpoint before anything has happened on the screen. And the reason is because if you think back to our initialization step, the last thing that the initialization step did was shuffle the deck of cards. So let's single step through this. Here, the value is 42. My index is 1. So I'm asking myself, is the 42nd element of this deck empty? Well, since this is the first time through, the answer is yes. So we come down here, and what we do is we put in the 42nd position the value of 1, and that's going to be the ace of spades. So card number 42 has now become the ace of spades. We up the index, we up the pass count, and we do the next iteration. We ask, is 2 less than the deck length 52? It's yes. We come down, and now val is equal to 49. And we ask, okay, is the 49th element of this deck empty? The answer is yes. So we assign 2 to the 49th card. So now the 2 of spades is card number 49. We increment the index, up the pass count, and we keep spinning through this. And of course, we're eventually, as this card deck becomes filled, and we place more and more cards in, this test right here is going to have collisions. We're going to find that there's already a card in that slot. It's no longer 0. So it's going to take longer and longer to fill in the 45th and 6th, 7th, and 8th, and 9th cards until all of the cards are placed in the deck. So this pass count will start spinning up rather rapidly as the card deck fills up. So let's go down, let's set a breakpoint down at the bottom and spin through the entire deck. And we can find now that it took us 249 passes through this loop to fill all 52 positions are all 52 cards in the deck. But when we get done, if we look at that deck object, you can see we have a 23 modulo 13. That would give us 10. So this is going to be the 10 of, I think it's the 10 of hearts. That would be the first card. This one's going to be the Jack Queen. This will be the Queen of Hearts. And this will be the 3 of Spades. So you can see how the deck of cards is actually now shuffled. It's in a random order. When we're done with this, we can return the pass count. We set next card back to 1 just in case we want to start over again. And let me kill this. We don't need to go through the program code. This is not the only way to shuffle a deck of cards, and I'm probably pretty sure it's not the most efficient way. But it has one saving grace. It works. So if it ain't broke, you don't fix it. That's why this code is what it is. The next general method is get card pip. We know it's a general method because it has a public access specifier, which means that we're exposing it as part of the user interface. So what we do here is we pass that in an index number, and so if we want to know what the 33rd card is in the deck, we can pass that in. We can go to that, look in the pips array, and find out what the 33rd card is, and that'll turn whatever this turns out to be card number 33. If this is 27, 28, 29, 30, 31, 32. So the 7 of diamonds would be the 33rd card in the pips array. If the index doesn't fall within greater than 0 and less than or equal to the deck size, then we have an error and we return nothing. Get one card is actually a method that simulates dealing one of the cards off the deck. To do that, we always increment the card first so that we're looking at the next card because the previous card's already been dealt, so we're going to look at next card. And then we say, do we have another card available? In other words, is next card still less than deck size, less than or equal to deck size? If it is, we return the next card. Otherwise, from the deck. Otherwise, we return 0, and that would be used to indicate that we're out of cards and you need to reshuffle. We could have put a reshuffle in here, but some games possibly don't want to reshuffle the deck. So we leave that to the user of this routine to decide whether they want to shuffle the deck or not. They can look at the return value of 0. If a 0 comes back and they need to shuffle the deck, they can test for that and shuffle the deck. Finally, down here, the returns get cards left in deck. This is nothing more than determining whether we have enough cards left to deal out is the deck size minus the next card. Because next card's always been incremented anytime we deal a card out. So we can tell how many cards are left by simply calling this particular routine. And right for this game as it stands right now, all of the functionality that we need from the deck of cards are handled by these relatively few general methods. The only complicated one really is the shuffle the deck one. The rest of them are simply manipulating the data that's currently being tracked in the class.